In this video, we'll look at the standard deviation, which is another way to measure the spread of a dataset. We've already seen two ways to measure the spread of a dataset: the range, which is the distance between the lowest and highest values, and the interquartile range, which is the distance between the quartiles, that is, the points 1/4 of the way and 3/4 of the way through the data. These are useful, but there's a third measure of spread that's even more useful and much more widespread: the standard deviation, which can roughly be described as the root mean squared distance from the mean. If you're not sure what that means, don't worry, we'll break it down. Say we start with this data set, 3, 4, 5, 6, 6, 7, 8, 9. We'll calculate the standard deviation step by step. Feel free to pause the video at any point if you need to catch up and see where everything comes from. First of all, we find the mean of the data, add up all the numbers, and divide by how many numbers there are. In this case, that's 6. Then we see how far away each data point is from the mean. For example, 4 is 2 below the mean of 6. We could write this as -2 to show that it's below the mean. But actually, the negative numbers won't really matter much anyway, because in the next step, we square all of those distances, which makes everything positive anyway. After we've done that, we take the average of all of those squares, and that gives us something called the variance. Notice that when we squared the distances, it gave greater weight to the data values further from the mean. So the more spread out your data is, the bigger your variance is. Finally, to get the standard deviation, all we have to do is take the square root of the variance. So here, that's the square root of 3.5, which is about 1.87. By the way, a side note, if you've ever been led to believe in your previous math classes that a decimal answer means you did something wrong, put that notion out of your head. It's pretty rare that we ever get a whole number for the standard deviation in the real world. Here's the formula for the standard deviation. Now, don't panic. This may look intimidating, but it turns out this notation just describes all the steps we've already laid out. First, we find the distance of each data point from the mean. Then, we square them. Next, we add up all of those squares. And then we divide by how many data points we have, which gives us the variance. Finally, we take a square root, and that's the standard deviation. If you're wondering about some of those funky symbols, that U-looking symbol that represents the mean is the Greek letter mu, while the O with the hook looking symbol for the standard deviation is the Greek letter sigma. Actually, it's the lowercase sigma. The symbol for summing things up is also a sigma, but this one is uppercase. Sigma, S, stands for sum. So it just means to add a bunch of things up. Now, wait a minute. Why are we using the Greek letter mu for the mean? Wasn't that supposed to be x bar? Well, there's actually a good reason for having two different symbols. See, one of the big ideas of statistics is that in order to find out some information we want to know about a population, we take a sample and analyze it in order to make a guess about the population. To keep things straight, we use different symbols for things we want to know about the population, which we call parameters, and things we can actually find from our sample, which are called statistics. So for the population, we use mu for the mean and sigma for the standard deviation, while for the sample, we use x bar for the mean and s for the standard deviation. And that actually leads to a small technicality we have to be careful of. Those steps we followed for finding the standard deviation are actually the steps for a population standard deviation. We're assuming our data is the entire population. But if our data is a sample, we have to make one tiny change to our procedure to find the sample standard deviation. When we're finding the sample variance, instead of dividing by n, we have to divide by n minus 1. This accounts for the fact that otherwise, the sample standard deviation would tend to underestimate the population standard deviation. In this case, since there are 8 data points, we divide by 7 when we find the variance, and therefore we manage to get 2 for the sample standard deviation. So just remember that when you collect data and you're finding the standard deviation of your sample, You need to find the sample standard deviation S, not the population standard deviation sigma. As I'm sure you expect by now, Excel can also calculate the variance and standard deviation with the commands var and stdev, respectively. Just make sure to put .s after each of them to use the sample formulas. You can put .p instead if you have an entire population, but for most things you'll be doing, you'll want to use .s instead. Let's look at one of the ways we can use the standard deviation. The first time I taught this course at GSU, I gave a survey to my students asking them to add up the total number of letters in their first and last names. When we looked at the results as a histogram, the data roughly resembled a symmetric unimodal distribution that's pretty common throughout statistics. Lots of data toward the center and less data at the extremes. We call this shape a bell curve, and the most common distribution that usually gives us a bell curve is called the normal distribution. We'll get to know the normal distribution much better later on in the course, but we're previewing it now to see why the standard deviation can be useful. If the data is normally distributed, then first of all, the mean will be right at the peak. That's because bell curves are symmetric. But here's what's really interesting. For any normal distribution, it turns out that about 68% of the data will fall within one standard deviation on either side of the mean. About 95% will fall within two standard deviations on either side, and about 99.7% will fall within three standard deviations on either side. This rule of thumb is usually called the empirical rule, the standard deviation rule, or my personal favorite, the 68, 95, 99.7 rule, because those are the numbers that always show up. So, for example, when we found the mean and standard deviation of our sample of name lengths, we got a mean of about 11.81 and a standard deviation of about 2.82. So to set up the empirical rule, we can draw a bell curve and then put the mean as 11.81. Then we repeatedly add the standard deviation 3 times, and then repeatedly subtract the standard deviation 3 times. Then the empirical rule estimates that about 68% of the class had names between 8.99 and 14.45 letters long, about 95% were between 6.17 and 17.45 letters long, and about 99.7% of the class had names between 3.35 and 20.27 letters long. So the takeaway is, if you know something is normally distributed, and lots of things in the real world are, from shoe sizes to cell phone battery life to income distribution, and you know the mean and standard deviation, the empirical rule lets you make some quick estimates of how likely you are to find data within certain ranges.